Alright, so I want to take a look at problems 5 and 6 on the acceleration problems. Alright, and so just to review really quick about acceleration and the equation we use to solve it. If you remember, we represent acceleration with a lowercase a, and that equation is equal to delta v over t, or our final velocity minus our initial velocity divided by time. Remember, your final velocity is going to be your ending velocity, or the speed that you reach, and your initial velocity is going to be your starting velocity, or the speed you start from. All right, so looking over at number 5 and 6, the first thing we need to do is read the problems and pull out the givens. So on number 5, it says a car with a velocity of 22 meters per second. So we already know we have some type of velocity moving at 22 meters per second, is accelerated at a rate of 23.1 meters per second squared. Anytime you see meters per second squared, that's going to be a type of acceleration. So that ms squared are the units that we use for acceleration. All right, and then it wants to know what is the final velocity. Oops, and I forgot the 20 seconds there. So if we were to make a list of givens, which is just organizing our information based on what the problem gives us. We know that we have a initial velocity because it tells us the car is moving at this velocity, and we are looking for final. So we can say our initial velocity is 22. Our acceleration, we know it's acceleration because it tells us it's accelerated, and also because of our units are meters per second squared, it's going to be 23.1. We know our time is 20 seconds because anytime we see seconds, we know that is a type of time. I'm just going to go back in and fill the units. All right, and we are looking for our final velocity here. So we need to ask ourselves, what's an equation we know that uses all 4 of these variables? It's only our acceleration equation, which is written as VF minus VI divided by time. We want to solve for VF here because we know our A, we know our VI, and we know our T. So we're going to work on isolating VF from every other variable in this equation. So I always start by my first step is anytime I have something in the denominator, I want to go ahead and move it to the other side. So to cancel out this t, we're going to do the opposite or the inverse, which would be multiplying it by t. That would cancel it here on our right side. And on the left, remember you have to multiply because it's all about balance. So we're going to end up with an equation that looks like t times a equals VF minus VI. All right, and keep in mind we're trying to get VF by itself. So the next step we're going to do to get VF by itself is add VI to both sides, because you have to do the opposite. And so that should give us an equation that looks like VI plus A times time, or T, equals VF. Right, and so from here, we're able to look at our list of givens and plug in our values. VI we see was 22. We're going to add 23.1 times 20. And if you remember order of operations, we multiply first before we add. So we should multiply 23.1 times 20, then add 22, giving you 484 meters per second. Since we were looking for final velocity, and remember, the units for velocity are just meters per second. So that's what our units would be for our final answer. All right, looking at number 6, we're going to kind of follow that same process. We're going to read it, pull out our givens, and we're going to have to do some more isolation of a variable in this problem. So this is a plane at rest. This is one of those key terms you have to look for when we're problem solving, because if something starts from rest, you know it's not moving in the beginning. So we could go ahead and label that as our VI. So our initial or starting speed is 0 because we're not moving in the beginning. It says it must reach a speed of 61 meters per second. So we're going from 0 to 61 meters per second. And remember, if there's no square on the seconds, that's a type of velocity. So our VF is going to just be 61. And it gives us an acceleration because, again, it's meters per second squared. It tells us its acceleration as well of 2.5 meters per second squared. And we want to know how long it will take to reach the takeoff speed. And anytime it asks for how long something will take, we're looking for a type of time. So now we've identified all the givens and we're identified what we're looking for. So again, we ask ourselves, what's an equation we know that uses all four of these variables? And that's going to be our acceleration equation, which is acceleration equals VF minus VI divided by T. So we're going to work on isolating our time. There's a few ways to approach this. I'm going to take kind of the longer route to do this just because I like to show step by step how we get there. But first thing is anytime we have something in the denominator that we're looking for, we of course want to get it off the bottom or out of the denominator. So to get T off the bottom, because remember we are looking for time, we're going to do what we did similar up here in problem 5. We're going to multiply both sides by T. So doing the inverse, remember what you do to one side, you have to do to the other. It's all about balance. So we should get time times A equals VF minus VI. So we are back in the same spot we were in problem 5. However, now we're wanting to get T by itself. So now that we've gotten T out of the denominator, we still want to isolate that variable. So we are going to move A to the other side. If you're multiplying by A, we're going to divide both sides by A to make it cancel. So we're going to get time equals VF minus VI divided by A. And so from here we can see we've isolated the variable we're looking for so we could plug in our values. Remember VF was 61, VI 0, and our acceleration was 2.5. So if you plug that in your calculator, you should get 24.4 seconds. Remember the units for time is just seconds. All right, and if you still have any questions after watching this video, please feel free to email me, reach out, or let me know how I can help you.